Voice is good. All right, so let's go ahead and get started. All right, so we have a choice here. Okay, so I don't have any additional material prepared per se, but I can actually talk about the clocked mechanism and why it is kind of really useful. Okay, so we can go that route. We can also go back to arithmetics and talk about division and multiplication and how to do it using a circuit. Okay, so we can go back and talk about that too. Or we can just kind of go over the solution to the homework assignment. So we have three directions that we can go.
Homework assignment.
I kind of want to know about the multiplication division.
Okay, so do we have one vote for multiplication and division?
Second that.
Second that? Okay. So let's do multiplication and division then. Okay. It seems like that's the majority already. It seems like that's the majority already. Okay, so we're going to talk about division and multiplication. So I don't have the slides prepared, but I can always use my document camera to show you, how the math is supposed to happen, and then we can translate that into logic sim designs, okay, which is going to be really kind of cool. All right, I am recording. Okay, so I am recording. So let's go ahead and go to my document camera. So the first thing we need to do is to find out how do we do multiplication by hand in base 10. Okay, I'm hoping all of you know how to do it. You don't have to do it fast. You just have to know how to do it. So let me adjust this a little bit. Put this here and refocus. Okay. All right, so let's do longhand multiplication by hand first, okay? So I'm going to use a concrete case, like 371 times 169. Okay, there we go. So which one to deal with first is kind of, I assume that part is actually a part of it, is convention. Because I always start with the 100, but I was told that some people always start with a unit. In other words, with 169, some people start with a 1, I start with a 1, and some people start with a 9. It doesn't really matter which one to start with because it is addition in the end. So I just start with a 1 and I say, okay, 371, 0, 0. And then we have the 6 times 1 here with the leading 0. 6 times 1 is 6, 6 times 7 is 42, and then 6 times 3 is 18, 18 plus 4 is 22. Okay, and then we add these two partial, products. 0 plus 0, 0 plus 6, 3, 9, and a 5. And then we have 9 times 1. 9 times 7 is 63. 9 times 3 is 27. 27 plus 3 is 33. Then we have a 9, 9, 6, 2, and a 6 here. So the answer is 62,699. Okay? And I'm never really sure about my own arithmetics. When I do it by hand, I make all kinds of stupid mistakes. So what we'll do is we're going to abuse a tool. And use a spreadsheet to help us do the calculation. We'll use the spreadsheet for other purposes later on. Okay, allow pop-ups. There we go. All right, so what we're really trying to do is to multiply 371 and 169. And I got the right answer, surprisingly. That surprised me, that I did not make a stupid mistake somewhere. Okay, so are there any questions about this longhand multiplication? Yep.
Do you prefer to be doing it like this, as in if there's a 1 in the beginning, start with the 1?
Doesn't really matter. Yeah. Whatever you want to do is fine. It's the same approach. It's just, are you starting with the least significant digit or are you starting with the most significant digit? It doesn't really matter.
I mean, there's a reason why you go like this.
It's just the way that I was taught. That was it. It's arbitrary, right? You can start from one end, you can start with the other end. It doesn't really matter. Okay?
I didn't go digit by digit rather than clumping them.
Hmm?
I
I actually tend to go digit by digit.
Digit by
like
digit.
1 by 9 and 1 by 6. You know, I tend to actually separate them into large columns. And
Oh,
then
okay.
And then I add
So
them
you
all
don't do the
together.
partial sum? You don't do the partial sum like this one?
No.
Okay, well, you know, it just makes it easier for me to do the partial sum, so I don't have to add up like many digits, you know, in the same column.
That's why I end up
Yep.
having to do a lot of times.
Yep. Okay, so when you look at it this way, what about in binary? Okay, can we do this in binary? But the same approach, right? So let's check out it in binary. Okay, so we'll check out 1011 times I don't know 0101. Okay, that's seems okay. Same approach, right? So I'm going to use the most significant bit to the least significant bit approach to mirror this approach over here. Is that okay? Sort of? Okay. So we have 0, 0 as leading zeros. But this time I don't have to do that, you know, kind of internal multiplication and the carry and stuff like that, because in binary, the worst you can get is 1 times something. If you're lucky, you get 0 times something. But the worst you can get is 1 times something, which means I don't have internal multiplications that I have to deal with. Like here, okay, 9 times 7 is 69, so I have to like write down the 63, sorry. So I have to write down the 63, you know, somewhere, you know, is it here? Oh, 9 times 1 is that, so the next one is 63, so I have to do the carry, I have to remember the multiplication table and all kinds of stuff like that. In binary addition, I'm multiplying this one to this number here. What do I get? 1011 with 2 zeros as least significant bits. Ooh, okay. I'm starting to like this already.
And then we go to the...
Yep.
Wait, how do you know there was only 2 zeros at the end?
Because I'm using this one.
Okay. Gotcha.
Just like I'm using this one over here, and that gives me the 2 zeros here. Okay? So the next one is a 0. I'm going to skip that. Is that okay? Or do you guys insist that I need to go for the 0?
It's not significant.
Well, it's not significant, but I can always just write down a whole bunch of zeros here. It doesn't hurt anything, right? Okay, so we say add. Okay, fine, we get the same result. Okay, now can we move to the least significant digit?
Yeah.
Sure. 1 times 1011, anyone? Oh, it's 1011. 0 plus 1 is 1, 1, 1, 0 with the carry, 1, and that's it. That's the end.
50.
Hmm?
It should be 50. It was 10 times 5. So I have to double check.
This one, okay, if you want to double check the math, 1011 is 11, and then 0101 is 5, so we should get 55. So this is 1 plus 2 plus 4, no 8, there's a 16 and a 32. So we got 7 and 8, so we get a 5, so we get, you know, definitely that 5 here. And then for the most significant digit, we got 3 plus 1, which is 4, and then plus the carry from the unit, so we do get 55 back. So it double checked and it works out. Okay? So are we doing okay so far with the approach? Okay? All right. So the next thing we'll do is not to use concrete numbers in binary. We'll use individual digits. So we'll go back to we'll have individual bits A, B, and C, you know, being the first number, and then we have individual bits D and F as the second number, and then we'll look at how those digits float around in the longhand multiplication. Is that okay? All right. Okay. So okay, this is what I'll do. I'm going to push this up as much as I can. We'll keep this one here just to remind ourselves what happened over there. But this time we have ABC as individual bits, DEF as individual bits, and we have a multiplication. Is that okay? Oh, but that seems kind of abstract. But what should we put on the first row if I were to address the most significant bit of the second number first?
D and then parentheses ABC.
Okay, well, it would be, but we can also do the individual multiplication. This is something that you can do in binary, but not in decimal. In other words, what goes here is going to be CD, C times D. What goes here is going to be B times D, and what goes here is going to be A times D. Those are the individual digits. You cannot do this in base 10 because base 10 can potentially have a carry from this into here, from here to here, and so on. So the digits occupying these places is not really just, oh, this digit is just this digit times this digit. That doesn't work in base 10. But in base 2, easy peasy, because the worst you can do is 1 times something. Is that okay? All right. And since an adder can only deal with adding two numbers at a time, I do need to know what is the next row. Okay, we have a leading 0 here. And what is this row going to look like? E times C, right? Or C times E, B times E, and A times E. And we'll just pad a 0 here. Is that making any sense? Because when we specify an adder, the two numbers need to have the same number of bits. So that's why we want to have this leading 0 on the second row just to make it a 5-bit number, just like the first one. Yep.
This is supposed to be CE on the second row.
On the second row,
Oh, it is
C,
C.
C times E. Good
He said
catch.
G, but he just wrote D.
Yep. That's how good of a liar that I am. I can do it without thinking, without flinching and giving up any clues. Okay, so that seems pretty easy, right? So now it's time to add. Okay, so after you add, whatever you get doesn't really matter. We'll just call this V W X Y Z. Okay, that's just the sum of the first two rows. Okay, what about the next one? Next one is going to be C times F, B times F, and A times F. And then we pad 2 leading 0s here. And you add these two 5-bit numbers. That's the final answer. Are we kind of doing okay so far with this calculation? Okay, so now we want to think about this and go like, well, can we convert this into a circuit diagram? We can make certain assumptions. We can assume that we can implement an adder, okay, any bit adder. In this case, we have we need 5-bit adders, one here and one here. Let's just pull from the library of Logicsim for the adders. Although we do know the equation to generate T5 or K5 for a 5-bit adder, it's going to look kind of long. Okay, so we're not going to waste the time to make that happen. So we'll pull the adders. The second question is, what about this multiplication? Isn't this going to be chicken and egg, because we're trying to implement multiplication, but we need to implement multiplication first? Well, almost. But because this is base 2, multiplication between 2 bits is just the same as and. Exactly. Can we do and? Logical and. Regular logical and. 2 inputs. Yeah, we can do that easy, right? So this is just A and D, B and D, C and D, A and E, B and E, C and E, and so on. So we've got all the basic components. Hold on a second here. Can we pad zeros? Okay, we know how to do this part out. We can do a multi-bit conjunction, which is handy. But what about these two less significant digits of 0? Do we know how to do that? And if so, what is the mechanism to pad zeros? We have 3 individual bits that has a source to come from, and then we have 2 bits that are constant, and they come from quote unquote nowhere. So how do we generate a 5-bit thing from a 3-bit thing? A splitter, very good. Good, exactly. So we just need a splitter. Feed it the constant of 0 as the least significant 2 bits. Give the other 3 bits from a multi-bit conjunction, and we're done with the first row. Second row, kind of the same thing, except we have to have the more significant digit of 0 as well. Once we have these 2 rows, we feed these into an adder. Whatever comes out of the adder is V, W, X, Y, Z, and then we have another pattern like that, except this one has got more. The bottom row has got 2 zeros to the most significant side, and then we have the multi-bit conjunction, or the result thereof, on the right-hand side. And then we add these two, and we have multiplication. Is that okay? All right, so I think we have the general idea of how to do this in LogicSim. Now it's time to go to LogicSim and actually do it. Okay, we will do it only for a 3-bit by 3-bit multiplier, but the concept can be easily extended to any bit. Okay. All right, so we'll go to a command line, start up LogicSim, Java. And this is also why I keep going back and say, if elementary schoolers understand, the simplicity of binary numbers, they will never go back to base 10, because to learn multiplication is a matter of, even for elementary schoolers, if they were never polluted by base 10 multiplication, this is easy to learn and easy to apply as well.
It's just really long to write sometimes.
That is correct. But you have to remember that we are already moving away from the time when the ability to carry out a 5-digit by 5-digit base 10 multiplication in your mind is prized. There was a time when we have competitions, okay, in specific cultures, I guess, that that prized the ability to carry out multi-digit base 10 multiplication without using a piece of paper. It's kind of like a spelling bee, except it's multiplication bee.
It's a math.
But that is no longer applicable as much in modern society. We have calculators, we have spreadsheets, we have all kinds of ways to do computations really fast. So I personally think it's a waste of neurons to train ourselves how to do those calculations really fast. Understanding the principle is important. But once you understand the principle, once you abstract the mechanism, then you use a computer, a tool, to do it. Is that making any sense? Okay? All right. So now we switch to...
If you know the concept, then if you don't have the tool, at least you're able to do it with anything.
Correct. Yep. So the key is to understand the concept first, and then be able to generalize and figure out the pattern. And that is something that we are still better at compared to computers. But how long are we going to stay ahead of that curve? I don't know. I do not know.
Humans are obsolete.
Well, at some point, by the time we can design technology that is capable of automatically refining technology to the next level, then we have hit the curve. We have hit the point where, okay, imagine that this part we don't have to record. So imagine, we have a curve like this, okay, and this is humanity rolling a ball, okay, uphill, okay. So at first it's really steep, okay. It will take hundreds of years to come up with the next invention, the next really, really important invention, which will bring along discovery of something that fuels the next, invention and so on. But once you get the ball up to this point, it's like it doesn't take much to roll it over to the other side. This is the point where you will have automated tools to design and refine and and innovate the next generation of tools.
What is humanity?
And all it takes
What's the purpose of humanity?
is a person to push this thing like that. At first, we wouldn't even notice it because the ball will start rolling by itself without people pushing it, or this person may still be pushing it for like this much, depending on how heavy the ball is. It may not gain speed very quickly. So the person here may think, oh, I still need to push it, okay? Not noticing that without pushing, the ball would continue to roll at that point. Okay? So by the time this person is over here, the ball is going to run all by itself. It's runaway. It's a runaway train. Okay? It applies, I think it applies to climate change, but it also applies to technology. So the future is interesting because we, on one hand, we might have an environmental issue that we cannot fix ourselves. Okay? There's no way that you guys will go out to the ocean and use a sieve to fish out all the broken pieces of plastic. Okay? Okay? Even if every single person on Earth is willing to do it, we don't have enough people to do all that. But by that time, maybe technology is also going over this curve here. So it's not going to be people doing it anymore. It's going to be robots doing it. But it's not just robots. Okay, you're looking at a mothership, an actual floating mothership that is fully automated, that can repair and manufacture those robots, the smaller robots, to do this collection. And at the same time, there'll be orbital data centers that can try to invent newer ways to design these robots. When the orbital invention generation machine comes up with a better design and say this is a much more effective way for robots to collect these debris from the ocean, it would just send the plan over to the mothership that is floating and go like, okay, all newer robots would use this new design because it's more efficient. Yep.
I was saying that's going to realize that humans were the cause of the climate change and take us out.
Well, that depends on whether the objective is to clean up or to address the root cause.
Just clean up.
If the objective is to clean up and the survival of the robot and also the mothership is to clean up, then it wants humanity to keep generating all these ways to justify its own existence. It will say, please use more plastic bags. Because I need to continue to exist. The moment it's all cleaned up, I'm going to be scrapped and do something else.
And they start destroying renewable energy plants, right?
Right.
They would start destroying renewable energy plants, right?
Yep.
So how far would that logic go?
You can just halt production.
You can hold production, but at some point, if it has self-preservation goals and stuff like that. Remember, it also wants to spread. A mothership may have the ability to very slowly construct another mothership, just so that if one mothership goes down because of natural disasters and whatnot, we have another one that is already assembled. Okay, so we're talking about replicators in SG1, Stargate SG1. But it's a matter of where is technology? Are we up here? I think we're still here. Okay, we are still up climbing the hill, but when it's going to cross over, it's hard to tell because it's not because of one technology. It's because of the interaction between technologies. Okay, it's one technology fueling innovation in another one in an unexpected way, and that in return fuels the advances of the first technology. So anyway, all right. So getting back to the boring stuff that we have to do. A 3-bit by 3-bit adder. Okay, so on one side, I have the implementation. Okay, I'm gonna do it like this, just so that I can have a little bit more area on the other side to draw the picture. Okay, so there we go. There we go. Okay, excellent. So we need a multi-pin input for ABC, which is the first number that we are multiplying. We'll just call it X. And it's a 3-bit input. Okay, let me magnify this a little bit. There we go. And we'll duplicate this for Y, which is the other number that we are adding or multiplying. So this is Y. Okay. So X is providing ABC, Y is providing DEF. Is that okay? So we are crossing over from the handwritten format to the Logisim format. Okay. So the first thing we need to do is to do there's no way around splitting Y into its individual bits because we need to do at the end using those individual bits. So we need to split that, and then this is can we do a multi-bit AND here? The answer is yes, but with a trick. Okay, so I'll show you why it is a trick. So Y needs to be split, so we might as well just do it now. go to a splitter. Okay, thank you. And split it to 3 individual bits, or however number of bits you have. We have to split all of those. X, on the other hand, doesn't need to be split. It can just be by itself. And just to make this easier to draw additional components, I'm going to put it side by side like that. Okay, there we go. All right. So getting back to A times D, B times D, C times D, we are basically multiplying every single bit of X using bit 0 of Y. Okay, but in order to make this kind of easy without using really individual gates, we can pull an AND gate here and turn it into 2 input, but each input has 3 bits. So it's a multi-bit AND gate. But that means this bit here also needs to be multi-bit. So we need to multiply this thing by itself to multiple versions of itself. And how do we do that? We need a merger, okay, or it's the reverse of a splitter. Okay, so we'll do a duplicate of this. Oh, we took the other wire too, which we do not need. So get rid of this. And this time we are going to reverse the direction, like so. And it doesn't look good, so I'm gonna, there we go, that looks better. Okay, so what we're gonna do is to pull this X and feed it here, and then we take 1 bit out of Y, just 1, and make it go here. Oh, too much. So now we have 3 of these things replicating itself. In other words, we are taking bit. Oh, I just did it in a reverse way. We are taking bit F here. Do you guys want it to be consistent? I want it to be consistent, so let's take bit 2 instead of bit 0. It's pretty easy to do. We just take out this one, and it is now consistent with the hand-drawn version. Okay, so whatever comes out of this is going to be a 3-bit number, which is going to be this portion. It is okay, but we need to pad 2 zeros before we put it into the adder. So we take this, and then we also need a splitter in this case. So we take a splitter again, and this time the splitter is going to be a 5-bit thing. Of the 5-bit thing, we want the least significant 2 bits to come from 2 individual sources. They can all be constants, and then we want the first 3 to be a bundle already. Okay, so the way to do this is to make the most significant bits bundled. Okay, so right now they're the bottoms, and then the top 2 would be the first 2 bits, and we want to split that into 3-way. Okay, so the bottom, 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 and then this is mid, and that is top. So is that okay so far? Does everybody understand why I split it this way? Okay. Then it's a matter of taking this, feeding into the most significant 3 bits, and then we just pull a constant of 0. Okay, this is a 1, but that's okay. We can change it to a 0 easy enough, and change the phasing so that it's easier to make the connections. So we have this one going here, this one going here, and here. Are we still doing okay so far? Is that okay? All right. So finally, we have one thing that is ready for adding. What is the next thing that we need to add? The next row, which starts with a 0, and then we have about the same kind of setup. So we'll kind of replicate the same kind of design here. So we'll go ahead and say, okay, we can keep everything from here to here, duplicate it, put it down here. But this time we're taking bit 1 to supply this portion. And then when we prepare for the number or the value to be added, we have about the same thing here, but not exactly the same thing. So I'm gonna duplicate the splitter just so that I don't have to specify it's a merger for 5 bits. But this time the way I split it is going to be the top and the bottom are individual, and then the 3 in the middle are the same. Is that okay? Because we need a constant of 0 for bit 0, we need a constant of 0 for bit 4 as well. But the 3 in the middle will just be the result of the conjunction with the AND gate, the multi-bit AND gate. Okay. So we take this and put it into here. And if I want to, okay. I'm just being lazy here. There we go. So finally, this is one of the numbers that I need to add, which is the top row. This is the other number that I need to add, which is the bottom row. So now I go to arithmetic and pull an adder. Okay. It's pointing in the wrong direction. This is going to look bad. Okay, so this is the adder. The adder has got all the components that we have talked about in this class. This is C in. This is one of the inputs. This is the other input. This is C out. And this is the actual sum. So we need to make sure that the carry in is a 0, because the only time when you don't want a 0 for carry in is when you're trying to stack adders so they can do multi-digit adding that is beyond the ability of a single adder. But in this case, we're just using an adder in the usual sense, so we don't have to do that. This becomes one of the inputs. And of course it doesn't like it because the adder by itself is an 8-bit adder. We change it to a 5-bit adder and it's all good again. Okay, we put this one over here. Carry out is not useful, so we will just leave it alone. And whatever this result is going to be VWXYZ. By itself is not useful because we need to prepare the bottom row first. So we're still doing okay so far with the logic design.
Still need to plug X into that bottom AND gate.
Say that one?
X is not in that bottom AND gate yet, the second one.
Yeah.
Oh, okay, gotcha. Thank you. There we go. Because X is ABC and that's why it needs to be here. Okay, that makes sense. All right. Any questions? No questions? Okay. So if there are no questions, we'll continue this particular pattern, and we'll just replicate this portion down here. And this time we are pulling the least significant bit of Y, which otherwise is known as bit F in the hand-drawn version. And hook it up here. And X goes to the other pin. And then we have another merger that looks about the same, but it's slightly different. Because this time the least significant 3 bits belong together, and then the most significant 2 bits are the individual zeros. So we have top, 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 and then 1, 2, split like that. And then the output of the multi-bit AND gate, we go to the 3-bit input of the merger, and then the constant of 0 will feed into bit 3 and bit 4, which are the most significant bits of the bottom row. Whatever is coming out of here goes into the next adder. So since I have this adder already configured, I just put one over here, and I just figure out that we don't have a space to pull that signal out. It would look bad. I can still pull it out like in this direction. It's just going to look bad. So we'll do the right thing and move everything over the other side one by one. So at least we can do it like this. Oh, we don't need it to be that long. Okay. So this goes here. And this one goes here. We still need a 0 to specify the inputs of 0 here. And let's see where we're going to pull that. This is a 0. I'm just finding a way to get it out. There we go. Looks ugly, but it should work. All right, so this is our result. This is the result of adding the last row to the second last row, which should be the product. So now we attach a 5-bit output pin to it. Okay, and we'll just call this the product of XY, or if you prefer XY itself is fine. Now we need to test whether it works or not. Right now we have 0, 0, 0 times 0, 0, 0, and the result is all zeros. Seems to work. So what number do you guys want me to test? What is the largest product I can get out of a 3-bit by 3-bit multiplier? 111 times 111, which is 7 times 7, right? 7 times 7 is 47.
49.
49. And can we store 49 in 5 bits? No, we cannot, because 5 bits only goes up to 31. The largest value you can represent in 5 bits is 31, so we can't. So that means we need to do something about this carry out. It is actually a part of the product. So let's separate this, okay, cut out this wire, and say that we need a 5-bit product. Okay, the largest product is actually 6-bit by not 5-bit. This gives me 5 bits. This gives me 1 bit. So that we need to somehow combine these two. So how do we combine those two? Merger. Okay, so we are just merging the carry to become the most significant bit, where the sum itself is the least significant bits. Okay, so we need another merger, same as a splitter, and this time it's going to be a 6-bit thing, but only have a fan out of 2. I don't know why it's complaining about this, but the fan out has the most significant bit all by itself, and every other bit to be on the same side. Oops. There we go. Does that make any sense? We've got to make it face the other way. So we want the splitter to face west, like so. So the 5 bits coming out of the adder forms the least significant 5 bits. The carry itself is our most significant bit. And then we connect these two. All right, let's check it out. 111 times 111 should be 49. And how do we write 49 as a binary number? 49 is, it's actually pretty easy, because it is 32 plus 16 plus 1. So that means we have a 1 here, we have another 1, and then all zeros, and then finally a 1. Okay, is that okay? So the way you can do binary conversion, quick and easy, for some values at least, is really just to write the value out as a sum of powers of 2. And for certain numbers like this one, it only involves like 3 powers of 2, which makes it kind of easy to figure out. Some of the other ones are more difficult because they're more powers of 2, but this one is relatively easy. So the result should be 110,001 when the inputs are 111 and 111. Let's check it out. 111, 111, and the result is wrong. Yep.
Don't you want to hook the C out of the first adder to the C in?
Nope, that one you do not need. Oh, you mean this part here?
From the first adder, there's like.
They should all be 6-bit adders. Yep, you're right. Okay, you're absolutely right. Okay, let me point out where my flaw is.
You have an unattached pin in your first adder, right?
Every single adder should be 6-bit wide, because when you add this row to this row, that can give you a carry already.
Yeah.
It's just that we didn't have that in our example. Okay, so let's go ahead and fix it. So that means okay, we'll start with the adders. Changing the adders to 6, because that will automatically invalidate everything else. So that's okay, because that helps to point out what I need to change. This needs to be 6 feet wide. with an extra 0 as the most significant bit. Now this is going to look really, really ugly unless I, take out the original thing first.
Yeah.
Yep.
Okay, why can't you just do the C out from the first adder to the C in of the second?
Because that will take this bit and add it here.
Oh.
So that's why we cannot quite do that. You can okay. So you are right that we don't have to use 6-bit adder here. So instead of using a 6-bit adder here, we can just change the second one. But it doesn't. This only works for the first adder. All the other ones cannot benefit from this particular thing.
So you have to take that C out and put it in the most significant digit.
Yep. Into the most significant digit of this sum here. So that means this thing needs to merge with that to become. So this will be a 6-bit adder. We have to change this splitter to handle 6 bits. So let's go ahead and take out the splitter first. Take out this wire, and then we make the splitter first. This is going to be a 6-bit merger and separate it into 4 parts. Okay, the 4 parts would be, the first part would be the first 3 bits, the least significant 3 bits coming out of here, and then the bottom 3 would be these 3 with an extra 0, so that should work. 1, 2, 3, but the most significant bit is going to be the carry out from here. Really, really ugly here. There we go. So we take out this wire and redraw this one. Like so. And then this one needs to be become a 6-bit bundle as well. So we take this out. 6 bits, fan out into 2, where the most significant bit is the one that is on its own. Everything else are bundled. This goes here. I don't need that little segment anymore, and I need to pull a 0 into here and 1 into here, and then the result is already 6-bit wide, so we don't need the merger. So we can take out this, take this out, and take out this entirely. There we go. Kind of convoluted way to do it. But that's the idea, okay? The next question is, if I have more bits to multiply, is it going to take more time?
Be the same process, right? Just
Using the
more
same basic
splits.
design, yep.
So no.
No, it does, yep.
So only the bit size will vary, right? I mean, the steps will remain the same. That's just.
The basic idea would be the same, but the number of adders would be increased. And this time there's no way to avoid the rippling because we are sequentially adding the numbers like that. Unless you have a adder that can take multiple inputs simultaneously, but internally you will still have to kind of do it sequentially. But this is the circuitry to do adding without using an algorithm. What about division? Do you guys want to do division? Well, let's do division. Since we can do 3-bit by 3-bit addition, let's do division. So in division, the first thing we do is to do it in base 10 first, the longhand version to doing division, and we can kind of re-experience how difficult it is so that we can appreciate base 2 division. Okay, so we'll have a division of 9, 6, 7, 9, 5, and we'll divide it by 176. Okay? It's not easy. Why is it not easy? Well, the first part is pretty easy. We look at 9 in the dividend and go like, does 9 contain 176? No. Okay, fine. We put a 0 here, put a 0 here. We do a subtraction. We get 9 back. Then we pull another digit here. Okay, 96. Do we have any 176 in 96? Nope. 0 times 176 is 0. Just like that. And then we move down here, 96. And then we have 967. This is a subtraction, this is a subtraction. So now we ask, how many 176 do we have in 967? Now this is the reason why base 10 division is not easy. Because in a division, you have a smaller division. So you can say, okay, so now you have to go through your mind and go use those little tricks that you have learned over time to guesstimate, okay? Does it have 6 of these? Or does it have 5 of those, right? 5 definitely works, okay? 6, no, 6 is not gonna work, okay? So this is how this is why it is difficult in base 10 division, is you have to kind of try out multiples kind of in your head, okay, in order to figure out, should I put a 5 here or a 6? Because it's sort of like, maybe, but the 6 is definitely too much. So we put a 5 here. And then the next thing you do is, oh, now we have a multiplication. It's a base 10 multiplication. So you cannot just say, oh, it's logical and. Nope, it doesn't work that way, right? So you have 5 times 6, which is 30. And then you have 5 times 7, which is 35. The 5 plus the 3 is 8 with a carry of 3. 5 times 1 is 5. 5 plus 3 is 8. So now you have 880, which looks right to me, okay? But that's not easy because we are using multiplication, and then we also have addition with carries and all kinds of stuff going on. Okay? So now we do the actual subtraction. So 7 minus 0 is 7. 6 minus 8 is 8 with a borrow. 9 minus 8 is 1. 1 minus this one is a 0. So we have 87 left. So now we end up with 879 divided by 176. So once again, we know this is 5, okay? But how do you know it's 5? Well, you kind of have to go through a lot of mental health, not mental health, mental math to do this, okay? It does affect your mental health if you do it too often, too many times. So it's 5, okay? But it's not easy. This is not easy at all. So 5 times 6 is 30. 5 times 7 is, well, it's the same thing, so I could have just copied it like that. And then you do the subtraction. Oh, dang. So we are off by 1. Sheesh. Okay, scratch that. Okay, see how difficult it is? Base 10 division with multi-digits. 4 times 6 is...
Negative effect on your mental health.
Yeah, well, it's definitely getting there. 4 times 7 is 28. So it's 30. And then 4 times 1 is 5. 4 times 1 is 4. 4 plus 3 is 7. There we go, 704. Okay. And then we... Okay, then we do the subtraction. 9 minus 4 is 5. 7 minus 0 is 7. 8 minus 7 is 1. Yep, off by 1. Okay, that checks out. Okay. Then we take this 5 down here. And now we go like, this is easy. Right? This one is pretty easy. It's just 9 of those. Okay. So 9 times 6 is 54. 9 times 7 is 63. And then 9 times 1 is 9. 9 plus 6 is 15. So 5 minus 4 is 1. 5 minus 8 is 7 with a borrow. 7 minus 5 minus 1 is 1. And we have 0 here. So that becomes our remainder of 171. I did not like this at all.
No, it's fine.
Okay. So, but is that okay? Does it remind you of base 10 multi-digit division and the pain of that? Okay. And once again, there are certain cultures that prize the ability to do all of this mentally without a piece of paper, and do it as quickly as possible. And then parents all send their kids to these special schools that will teach all kinds of tricks, and they will practice hours upon hours to do this kind of mental health as quickly as possible. There goes mental health. Yep. This would be a good thing to do. Actually, I take it back. Okay, this is the kind of thing that you want to do when you're having stress. Okay, like you're getting pissed off or something is really, really bothering you. Instead of thinking about what is bothering you, which makes you even more anxious and angry or whatever, you say, okay, I'm going to do this calculation here. Because the moment you do the calculation, guess which part of your brain takes over? The neocortex, right? Your new brain, only your new brain can do this. What makes you angry? What triggers your whole body to prepare for fight or flight or freeze? That's your lizard brain, right? It's called a lizard brain because it's the oldest part of our brain. So which portion has control determines, are you collected, calm, and are you thinking logically, or are you in a rage, okay? You're doing things that you probably will regret later on. Okay? Right. This will bring you back because it forces your brain to go back to your neocortex, because your lizard brain doesn't know how to do that. Now, ask any lizards to do a division, and you'll find that what? So I stand corrected. Okay, doing this at the right time actually improves mental health, but doing it too much may affect your mental health as well. Okay, so since we are talking about being logical, let's do base 2. So base 2 is a little bit longer. Okay? We need more digits to represent the same value. So I'll just throw in a whole bunch of zeros and ones. Okay, that looks good enough. And then we'll have a divisor that is, okay, how about that? Okay, fine. Okay, oh, okay, sorry about that. Yep, there we go. Okay, so it looks kind of daunting, right? Just coming from the other division, we go like, oh man, this is going to be awful. But it's not, okay? So we'll do the same thing here, okay? 0 times, how many of this, the divisor, do we have in 1? 0, easy. Okay, we got 1 here. Pull that 0 from here. How many of this do we have in 1, 0? How do you know that's 0? Okay, this part is all easy. So I'm gonna skip all this to the one that matters. Okay, right here. So we got 0, 0, 0. Okay. How do you know that's one of the divisor in this portion of the dividend? How do you know? Did you have to go through a mental division or mental multiplication to guesstimate?
It's a 6-bit divisor.
You need one more.
I need one more? Okay. Counting bits. There we go. Okay. So how do we know there's one of this in here? Oh, by the way, how many options do we have? In base 10 division, we can go anywhere from 0 to 9 to fill in a single digit in the quotient, right? Over here, how many choices have we got? 2 choices, 0 or 1. Oh, okay. That seems to make things a lot easier, right? In base 10 division, you kind of have to go through mental health. I mean, this is mental health. You have to keep going through. have to go through mental math, okay, to figure out how many of these things. Okay, you can probably get to the approximation like between 4 or 5, and then you have to go through the actual multiplication to get to, is it 4 or is it 5, right? In base 2 division, it is either 0 or 1, but how do you decide whether it is 0 or 1? You use a mechanism that we have talked about already. What is it? Comparison. That's all we are doing. There's no hidden division whatsoever. It is just comparing. In other words, at this point, we are comparing the divisor with the part of the dividend that we have constructed at this point. But it's a comparison. Which one is smaller? Is the dividend? Well, okay. The actual question is the dividend smaller than the divisor? Because if it is smaller, then you use a 0 as your quotient. If it is not, you use a 1 as your quotient. Isn't that easier? It's just comparison. So why is comparison faster than figuring out what is the multiple of this that still fits in here?
Less mental health.
Mental health, exactly. But why is it easier? Because the comparison is easy. You just compare the numbers from the most significant digits to the less significant digits until you find a difference. Or until you run out of digits that they're the same, right? But the other one involves not just comparison. It is actual division, okay? So, right here, we can say, oh, we got one of these, okay? And then you just write it down here, 1, 0, 0, 1, 1, 0, 1. You do a subtraction. But this is a base 2 subtraction, which is relatively easy. And the best part is you only get 1 or 0 as your quotient, which means there's no hidden multiplication to deal with this, to go from here to here. It is a bitwise AND. It is a multi-bit bitwise AND to go from here times this to get here. All right, subtraction is probably the only really difficult part is binary subtraction, which we already know how to do. So 0, 1, 1, 1, 0, 0, 0. So we put another 0, put another 1 here, and you can use that trick. Okay, we know there's none of this. Put another 0 here. We put another 0 here. We put another 0 here. We put 1 over here. Okay?
Yeah, there's the one minus. Oh wait, there's this one.
Okay.
You're wrong.
I think I already forgot binary subtraction. You said 1 minus 1 equals 1.
Okay, 1 minus 1 is 0. 1 minus 0 is 1. 0 minus 1 is 1 with a borrow, right?
Borrow.
So 1 minus 1 is a 0. 0 minus 1 is 1 with a borrow, and that's a 0. Yep.
The divisor doesn't match up. You have 1 0 0 1 1 0 1.
I copy wrong.
And then on the first line, it's 1 0 1 1 0 1 1.
Oh.
Oh, the divisor? You mean this
When
one?
you multiply above.
That's right.
This one?
Yeah, that
That's
line.
a dividend part.
It's a different number.
It's dividend. It's partial dividend.
It's full dividend.
This is from.
Divided by 1.
Huh?
Which is itself.
I don't see any issues.
This part.
Never mind.
Itself
Oh,
is
okay.
1.
So are we still good?
Yeah.
Okay. All right, so we got one of these, so we just write down the number here, 1 0 0 1 1 0 1. Do the subtraction, which is the most difficult part of this entire process. 0 minus 1 is 1 with a borrow. 0 0 0 minus 0 minus 1 is 1 with a borrow. 1 minus 1 minus 1 is 1 with a borrow. 0 minus 1 is a 0 with a borrow. 1 minus 0 minus 1 is a 0. Okay. 1 minus 1 is a 1. Okay, something is not right. Oh, that's a 0 here. Okay, there we go. Okay. So you get 1 0 0 1 1 1, and then you pull that 1 over here, and it is a 0 because, oh, it's a 1, sorry. I compared it in the wrong direction. There's a 1. So we got 1 1 1 0 0 1 1 0 1. This is an easy one. Yep, there you go. And then the rest, we just kind of pad down here because we don't have enough digits in dividend anymore. So these are all zeros. And so this is with a remainder of 1 0 0 1 1 in base 2. So despite, it looks kind of lengthy, and the difficult part is lining up the bits, and stuff like that, but not necessarily the process. The process itself is easy because it's all just compare. Do we have at least one of these? No. Okay, skip, pull the next digit down, and so on. Okay. Well, first of all, is the math right? Okay, that's the question. What is this value here? I'm not going to do it by hand. So we're going to use the spreadsheet. Okay, let's go ahead and use a spreadsheet to do this, because we got bin to dec, binary to decimal. So we can give it a string. In this case, it's 10110111001011. And I think it wants double quotes, not single quotes. That's the only reason.
Maybe you try removing the quotes.
You're giving it a string instead of a number, I guess. Sign finding.
It says the maximum length is 10 characters.
Microsoft.
You can just do it.
No, this is not Microsoft. This is a Google document. Microsoft doesn't even bother to give you binary to something conversion. Yep. Okay. Well, let's see.
What's the most significant?
There's online calculators.
Yeah, but I want to make my own. Okay, this is 10110111001011. Okay. Okay, so how do we make a calculator to do this? Okay.
Excel.
Okay, come on, guys. Okay, so let's use one column to spell out which bit we are talking about. Okay, so the right way to do it is to say this is the cell before +1. Okay. So we just need to have as many bits as we have in the number, and the number has got 1, 2, 3. Okay. It's only got 14 bits, so we have enough. All right. So the next column has to extract one bit out of the entire thing. Okay. So we can say, let's extract one bit. I think the function is called mid, and the string is this original string. The index start with. The only thing I have to really remember is it's one. One is the start. So we have to say 1 plus this number. I don't know. But this is how we can extract one bit out of that number. Come on, replicate. Doesn't want to do it. Huh. That is odd. Oh, it did replicate. It's just using the wrong string, that's why. Okay, so the string itself needs to have a $ in front of the row number, because otherwise that gets replicated too, which is the reason why it's not working. There we go. So I have just extracted the individual bits, right? So now we need to figure out, okay, what is the multiple of 2 that we want to multiply to that bit. So this is start with 1. This is whatever is before times 2.
It's actually, you're starting from the beginning. 0.
Oh, it's the other way around. Okay. I'm looking for a quick way to fix this. Because bit 0 is the most significant bit. It's the other way around. I want a closed form. I want a closed form. So let's do a power of 2. Okay. Equals power of 2 to the power of the string length of this string minus this column. Okay, does that give me... Okay, we don't have length. LEN, just length. Yep, okay, that works. All right. So we got the number of digits minus 1. So it has to be -1 here. And then the string itself needs to have a $, to specify that it is the same string. So I think that should work. Yep. Okay, very good. So the next one is just to indicate how many of these do we have to do the actual multiplication. So we can now say, I think this time it's going to be okay because it's just 0 or 1 times the actual power of 2 on the other side. Okay, so now we got all of these, and now we just need a sum of all the previous rows, like so, and we got the value. I mean, it's what I'm trying to illustrate is, you can make your own tool. Okay, if there's no tool to do something, you figure out how to do it, and a spreadsheet is a really flexible tool. It has got a lot of power to do stuff like that. Okay, what about the next number? So I'm gonna put this number here, 11723, and what about the divisor? The divisor is a smaller number, and I think this one we can even do it by hand. So the divisor has the value of, okay, I'm just gonna write it down here. It's 1 plus no 2, there's a 4, there's an 8, and the most significant bit is, let's see, 1, 2, 3, 4, 5, 6, 6 zeros. So 2 to the power of 6 is 64. So we have 13 plus 64, which is 77.
That's my guy.
Okay, so sounds like 77. All right. So now we go back to the spreadsheet and carry out the actual division. We want to figure out both the quotient and also the remainder of the division. The quotient is really just the floor of this number divided by 77, and it's supposed to be 152. The remainder is mod, and we start with the same dividend, and we have to give it the same divisor, which is 77. So that is the remainder, this is the quotient. So now the question is, are we getting 152 as our quotient? In other words, is this giving us 152? So let's figure out what powers of 2 do we have here. 0, 1, 2, 3. So we got an 8, we got a 16. That's 16, 32, 64, 128. What is that?
36 plus 16, which is 152.
Is that 152?
Yeah.
Okay, so we got the right quotient. So now the next part is this one. Is that 19? 16 plus 3, that's 19. So surprisingly, we didn't mess up the binary division at all. Well, I messed up a few steps, but we fixed that. Cool. How do we put this into gate logic? How do we do this in logic sim?
So we have to do subtractions and add it.
Yep, we have to do subtraction and we have to do comparison as well.
Comparison, right.
Okay, so let's go ahead and okay, so I'm going to push this up as much as I can, and then we'll try to do just one level. Okay, so we have some bits here. Okay, we have this is dividend. We'll make A, B, C, D, E, F. Okay, 6 bits for the dividend, and then the divisor is X, Y, Z as individual bits. Okay. Can we skip the first 2 digits for the quotient? In other words, can we just assume this is 0, this is 0?
Yeah,
We cannot. What if X, Y, Z is 0, 0, 1? Any number divided by itself is the number itself. So we cannot really shortcut the whole thing. Okay. So that means we need a quotient digit here. So I'm going to put a quotient Q1 here. Okay. So how do we determine what is Q1? Q1 is based on the comparison of which two numbers?
A and Z if X and Y are 0.
Exactly. We are comparing 0, 0A with XYZ. Is that okay? But what is going to be going into Q1? So let me put it on the side here. So we know that the comparison between 0, 0A, these two zeros are padded, versus XYZ as a bit pattern. The comparison of this is important. But how do we decide whether Q1 should be a 1 or a 0? Which way should we go? If 0, 0A is, if XYZ is less than or equal to 0, 0A, then the quotient Q1 is a 1. Okay? But we don't have less than or equal to in the comparison. Of all the flags that we have, we don't have less than or equal to. This is unsigned, by the way. Everything here is unsigned. So with unsigned comparison, we only got one thing that can help it, right? It's the borrow. Okay? The borrow flag after a subtraction indicates whether the minuend, which is the first number, is less than the second number, which is the subtractor. Is that okay? So the question now is, can I somehow use the borrow bit of a subtraction and some additional gates possibly to come up with Q1? What do you think? Okay, so let's work this out step by step. Okay, so we are saying that if 0, 0A is greater than or equal to XYZ, then we want Q1 to be a 1. Is that making any sense? Okay. But we cannot do greater than or equal to kind of comparison, but we can do less than. Okay. Isn't this the same thing as not 0, 0A is less than XYZ? We can do that. Okay, because the less than is indicated by the borrow flag. So that means Q1 is really the negation of the borrow flag after that subtraction, after the 0, 0A minus XYZ subtraction. Is that okay? All right. Okay. So Q1 is just, you know, the negation of the borrow flag after we subtract XYZ from 0, 0A. But remember, we have to put whatever is Q1 times Z here and do that subtraction, right? Well, whatever Q1 is, I just pull Q1 from here after figuring out the borrow flag, and then we take Z, which is the least significant bit, and then we do a bitwise AND. We can do that. It's just a bitwise AND. So now this bit here is just A minus Q1Z. That's a real subtraction. There's no way around it. Is that okay? Then what do? Then we pad a 0 here, and then pull the B here. Yep. And how do we do this? How do we get this 0B done as the other value to compare? A merger. So we are looking at each individual step and ask the question, do we have the mechanism to do it? And the answer is yes. Because can we do this? Can we make a 3-bit number using A as the least significant bit? Easy peasy. You just use a splitter as a merger, make the most significant 2 bits zeros, and then just copy whatever A is here, which is an input pin, to the least significant bit. We can do that. How about XYZ? Oh, that's easy. XYZ is an input pin. We just take the whole thing. How do we do this comparison? Subtraction. Okay, we know how to do subtraction. So we just do a subtraction, and then we look at the borrow flag after the subtraction. Do we have a borrow flag? Do we know how to calculate the borrow flag after a 3-bit by 3-bit subtraction? Yeah. Yep, that was a homework assignment. Okay, that's T3 in your homework assignment. And this is a negation. Okay, it's just a bitwise NOT. Okay, we have bitwise NOT gates, right? So we know how to figure out Q1 already. And then in return, we use Q1 and multiply that to Z. So technically, arithmetically speaking, it is a multiplication. But in Boolean algebra, that is also conjunction. So we're just taking one bit here, which is calculated using this equation here. We take another bit here and do a bitwise AND using a single bit gate. So now we have that. Now we have a subtraction. The subtraction is between the bit A and this bit, which is the result of a conjunction of Q1 and Z. But we know how to do subtraction. There are subtractors. This is whatever is coming out of the subtractor, the result of the difference. Okay, the difference is a single bit in this case, but in all the other cases, it's going to be multi-bit. And then we just pull whatever bit is also in the dividend, the next bit in the dividend to here, and merge these two into a 2-bit number. We have one bit number, and then we have. What do you think about this? We do the subtraction. And then we do that. Oh, okay, so we do the, we put a B right next to it. So these two is basically an addition, but it's not an actual addition. So take that back, we put a B here. So we merge these 2 bits into the next number, and then we repeat the trick. We look at these 2 bits as a single number and compare that to 0, Y, Z. Repeat the whole process. Do you see the pattern? You know, how we perform each step? So each step along the way is the construction of a multi-bit number and compare that multi-bit number to the divisor. We use the borrow flag after the subtraction to indicate what is the proper quotient bit. Okay? And then we take the quotient bit back, multiply the quotient bit to the divisor to perform the subtraction. After the subtraction, we take whatever difference is the result of the subtraction, merge it with another bit from dividend itself, and then repeat the whole process. Yep.
So, why can't it be ABC subtracted by Q1, X, Y, Z? Wouldn't it all 3 of them align straight down?
Say that one more time?
Why isn't the X, Y, Z right underneath the ABC like as
Because X, Y, Z can be 0, 0, 1.
right? So when you place Q1, wouldn't it be the 3rd bit, which would be AB, the C?
Yes, but we know that in this case, you know, X, Y have to be 0. So we just kind of shortcut it. Yeah. But technically, yes, you know, it is the entire X, Y, Z. But we know that, you know, this Q1 cannot be a 1 unless X, Y are zeros already. So that's why we can kind of simplify this one. But you can add more zeros, you know, in order to make this 0, 0, A minus X, Y, Z. But it wouldn't change anything because, you know, in order for this one to be effective, Q1, if Q1 is a 1, that means X, Y are zeros. So it's not gonna help do anything differently. But if you want the thing to look uniform, then you can use that way. Right? Are there any questions about this? The mechanism of division. We haven't really looked at the actual gate logic to do it. You know, maybe we can use the next class. But the next class we're going to look at the practice exam. So we're not going to get back to this after the practice exam on Monday. Okay.
Will you make a module for this?
Yeah, I will. Yeah. In which I will just, you know, take screenshots of my own document camera and use the Google closed captioning, you know, and copy and paste it as text. It will look like a ransomware. But yes, I will, summarize all of this and give you the actual, equations, and we'll also figure out the gates too. All right. Well, we don't have any outstanding homework assignments, but I will go to the lab and show you how I would write that program that you just turned in today. Okay? Sorry?
Gotcha.
Okay. So we'll take a short break and then we'll start at noon over in the lab.